Welcome to a read along with Dr. Pal in the book Discrete Perspectives in Mathematics. This is section 6.2 on determinants. All right. So, what is a determinant? A determinant is something we can do to a square matrix, like a 2 by 2 or 3 by 3 or 4 by 4 and so forth. And it's going to be similar to the idea of area or volume, although it can be positive or negative. We'll be seeing a little bit about that as we go, but for some motivation to begin with. Suppose we have two vectors, or two tuples, 1, 0, and 0, 2. We can list them out as columns, 1, 0, 0, 2. And if we were to graph them, so 1, 0 is like a tip, and the origin, say, is right here, and 0, 2 is another tip, it would look like this. You could think of 0, 2 as being 2 times E2, where E2 is 0, 1, and E1 is simply 1, 0. Okay, now we have this green area. Now look at this picture right here. What if this is completely green underneath, and these are two white triangles, and we take this white triangle and we slide it over here? The amount of green area is going to be the exact same here as here. Well, how do we slide that over? That's simply by taking this guy right here and adding a multiple of this guy. So if you add a multiple to it, you use the tail to tip principle, and you take this, you lift it up here, and then you can keep or you can keep going a different multiple of it. You add this to this, so this will bend this line over here. In fact, if we added 3 times E1, so 3 over, then it would take us to here. So it'd be like this. Now the area involved is the exact same here between this vector and that vector as a side as it was before. So by sliding kind of within these two parallel lines, we have the exact same area. And all we've done is simply added a multiple of one vector to another one. So if we have two vectors to begin with, and we add a multiple of one vector to another one, that's the same thing as sliding, and it preserves area. Now, so let's think about this idea of having area between two vectors from the origin, and then making a parallelogram out of it. All right, so let's just think of that idea of area. That idea of taking area from an established base vector, so let's just pick one of our vectors to be a base. Like here we have a base vector. Okay, so that's just going to be fixed here. And there's different things we can do from the base. Maybe we can come off with a vector u, or maybe let's just translate the base to right here, like this right here is the same as this dotted line, right? This dotted line between this point and this point is the same as here to here. And we can take a vector v off the base. So we can have base with a vector v or base with a vector u. Now this diagram actually shows us that the process of going from taking a vector to the base to an area for that base actually preserves addition of vectors. So if we, for instance, so let's make a function here like f of u plus v. And what does this function do? This function is defined for this particular base vector. So you have a base vector, that one stays the same. And u plus v, you throw it in, and then you find out what the area of this is. Now, what this is saying is that this right here, f of u plus v, is actually going to be equal to f of u plus f of v. Okay, well, I'm using this vector notation, but for arrow vectors, but So you have u plus v is going to be this u plus v here. And let's think about that. If we just use the u off the base, we get this green area. If we think of the base and lift it right to right here, and we go with v right here, this green area is going to be, so this green area right here is f of v. So this top area. And this area in here is f of u. Now notice by sliding, so you can slide between parallel lines, you can slide so that this green part would come in here and this green part would come in here. So we can see that right here. We slid it in and we notice, yes, indeed, off this base, u plus v is this area right here, and it ends up being the sum of this green area and that green area. Not only is it just with sums, but you can also visualize it with subtractions. Because if you have your base vector being here, and then your other vector is not, instead of being counterclockwise, just, acute kind of up here, it's clockwise down here from it. If it's below the base, we're going to say the area is going to be negative. So this region right here, colored as so, up here, is going to yield a negative value. So imagine that's being a negative area. And let's suppose that V is this whole thing from way up here, this whole big green thing that kind of goes over this base thing. So imagine it being right here. This whole thing right here is the area, or is like f of V, and this area right here is like f of u, and f of u is negative. Now, so if you take big F, so if you take this big piece and you subtract this piece off of it via sliding, you should end up with this piece, which you could slide over here, which ends up being f of u plus v. So even with subtractions, we actually get that this is a function that preserves addition of vectors. Finding area, as soon as you've established a base, you can actually get the area. Now, this is kind of a neat idea for computing determinants. Let's look at this particular case. Suppose we have a vector here, 3, 1. Suppose it's the base, and a vector coming off of it, 2, 4. So with assumption that this is a base, then if we're over here, we should have a positive area to begin with. But let's use the idea that it preserves addition. So let's take the vector 2, 4 and split it up into two parts that add together to equal it, 2, 0 and 0, 4. See this 2, 0 and 0, 4. So and notice that 2, 0 is below the base and 0, 4 is above it. So all we have to do is find the area of this piece and subtract the area of that piece, and it should be the area of this one. Now, a nice way of getting these areas is by sliding. Notice this parallelogram, we can slide into a rectangle right here. And so you get 2 times 1, an area of 2. So you can be subtracting off an area of 2 here. And this area up here, this parallelogram, you can slide into a rectangle here. To get an area of this rectangle, be 4 times 3. And then remember, that's a positive. So 3 times 4 minus 2 times 1 equals 10 as your area. Now, if we had listed off the base vector first, and then the vector that comes off of the base, 2, 4, notice what we've done. We've taken this 3 multiplied by 4, and then we subtracted off this 2 times 1. So kind of in a pattern like this. So we've taken 3 times 4 and subtracted off 2 times 1. This is true for 2 by 2 matrices. We have this idea of this diagonal multiply minus that diagonal. Okay, as long as the base vector from where we're working off happens first, and then the one coming from it happens next in columns. Okay, so that concludes this first little subsection. Thanks for watching.